Thermal inertia from the sun is a necessity for life on Earth. Solar energy hitting the Earth is stored in the Earth's crust and the oceans. Otherwise, we would be snap frozen at night from the very cold influences of outer space. Insulation from the atmosphere alone will not be enough to hold the heat. This storage temperature keeps the Earth's temperature in range for life, day and night and throughout the season. In the same way, on a smaller scale, heavyweight materials and water can be used to store thermal energy. For example, bricks, concrete and houses have high thermal storage capacity. This means that heat storage can be carried over till the next day, eliminating or greatly reducing the need for additional energy boosting. In utilizing natural storage strategies, it's worth knowing that water can actually store twice as much energy as concrete. We call this process mass linking. So how can thermal storage be used for renewable energy? As predicted by battery manufacturers, new, cheaper, reliable storage systems are on their way. The life cycle costing of batteries is still 2 to 3 times more than bulk peak rates. So how can this storage issue be improved economically? Battery storage costs are reducing, but they need to come down a long way. What if energy storage costs nothing? Or almost nothing? By storing thermal energy by mass linking in buildings or in hot water tanks, there is a way of storing PV energy for use over 24 hours. It can be used to store PV-driven heat collection from a DC connection or AC to a heating element or heat pump. There are many other ways that mass linking can be adopted. Experience in manufacturing hot solar water heaters since 2011 led to a decision to make a truly sustainable solar water heater that was far more reliable and economic. We took a totally different approach to what applied to most solar water heaters, which gained their heat from solar thermal panels. These old solar systems supply hot water to roof-mounted horizontal tanks. Our invention, called SolarTank, takes a different approach and incorporates a mains pressure heat exchange system using parallel coils. The tank is located at ground or floor level, thus avoiding the installation and maintenance issues, usually associated with roof-mounted systems. Smaller pipes in the heat exchanger increase the surface area to volume ratio for better heat transfer. Tests have shown that efficiency is 95.4%. With heating of cold water from the outlet to the required temperature at the tap, it is actually 28% better in this transfer compared to other heat exchange systems that are sometimes used. It also results in a 10% reduction in water usage. The tank is made of plastic with rib-walled profiles, creating bubbles of air between the shaped insulation, improving insulation of the tank dramatically. All the penetrations are from the lid of the tank and eliminate the need for any wall penetrations. This also reduces manufacturing costs, eliminates metal fatigue, and corrosion problems that are normally associated with hot water systems. The primary heating fluid is treated water. The tank is open-vented, so there is no pressure at all in the tank, and this greatly increases the longevity of the tank. PV panels supply electrical power to a suspended underwater electrical sheathed cable that is connected to a DC or AC element located near the bottom of the tank. This is the main source of heating during daylight hours. A heat pump system can be an alternative approach to heating via the central control pipe at this position. The booster element is an off-peak power AC resistant element that can be active during off-peak daytime periods when there is a glut of solar energy or renewable energy in the grid. Energy costs added are traded off against the main grid-connected PV system for credits achieved during daylight hours. This ensures that SolarTank is directly heated by the DC element during the day and time-clocked to boost the peak at night, costs being offset by the grid-collected credits for use of the owner's solar system during peak daylight periods, as well as a lower rate when not. This makes the energy bills as low as possible and the capital costs for systems competitive in the marketplace. The product is predicted to last at least 20 years, but will probably last 50 to 60 if maintained properly. It is a unique invention and should be a game changer when fully commercialized. Introducing MassLink. Air conditioning has had increased usage in buildings over the last 2 decades in every residential area in Australia, as well as other countries. Apart from the high cost of installation and maintenance, the energy used is now a major concern in relation to emissions resulting from fossil fuel power sources. Our invention, MassLink, was devised to lower the need for air conditioning and operate the system during daylight hours, using PV power and utilizing thermal inertia as a night storage medium to maintain comfort. The MassLink system is different to mainstream parallel plate type heat exchangers that to date have always been applied to thermoelectric cells, or TEC, cooling systems. This TEC system is a solid-state electronic heat pump that's already in use in many specialized applications such as computer cooling, military vehicles, and the heating of spacecraft. Our unique and novel design rely on especially configured tunnel heat exchangers made from aluminium. They achieve efficiencies unheard of in most applications to date, are predictable by theoretical physics, or the TECs as they are commonly known. It works using a system of specially designed aluminium tunnels with the air being heated and cooled via the tunnel itself, and the fins inside for high efficiency. The small TECs can be DC connected straight to the dedicated PV panels. The way the power is supplied, the airflow rates involved, the thermal isolation of the tunnels all assure the maximum energy from the TECs is captured in the system. Exhaustive testing and analysis has confirmed the efficiencies claimed in our patents. The heat rejection part of the system is similarly linked to the cell via these same type of air tunnels. The cavity wall of the house and thermal inertia in the external leaf in the perimeter of the cavity wall. This uses part of the MassLink operating system. As a result, we have named the wall system MassWall. The MassLink package unit is very neat and visually acceptable compared to normal wall-mounted air conditioners. An upward-facing pelmet is fitted to the return inlets near the ceiling level and distributes the air in the room after first passing by the mass in the wall itself. It may be simply a projecting panel or wall projection. It's up to the architect or interior designer to come up with a pleasing aesthetic. The visual potential is much better than the usual wall-mounted systems or ugly bulkheads that usually occur in most designs. The system can be retrofitted as part of a cavity wall construction or built as a special mass wall configuration as shown in this presentation. The last 4 years of innovative investment have been interesting. The motto of Innovate Australia is ideas into value. But I would say that the first step is to come up with not just ideas, but good ideas. What are the advantages of our new technologies from a local and global perspective? Let us explore the basic facts behind the innovations described in the video. The current cost of battery storage is simply not competitive against thermal applications. The 12-year life cycle costs of lithium-ion batteries in WA is currently 33 cents per kilowatt hour, when off-peak power is currently about 8 to 22 cents per kilowatt hour. Thermal storage is much cheaper than battery storage at present, and likely to stay so for a long time, probably forever. In other parts of Australia, off-peak rates are even cheaper. The grid acts as a very reliable virtual battery for grid-connected solar. Therefore, battery costs need to be reduced 50 to 60% to be viable, but they are ideal for nighttime general power and lights. Batteries will never compete with storage for thermal applications. Thermal storage systems are simply perfect for thermal applications. They don't need batteries in grid-connected areas. So let's look at the facts behind SolarTank. For providing hot water, life cycle assessments indicate 2 to 3 cents a kilowatt hour over a 60-year period, also 5 to 6 cents a kilowatt hour over a 20-year period. Both life periods are very attractive. We are using a 40-year life with 4 cents per kilowatt hour cost for all our comparisons. As shown at Murdoch University, the life cycle costing for a conventional solar water heater is 18 to 24 cents per kilowatt hour. That versus 36 cents per kilowatt hour for a conventional gas storage system. Therefore, we can see a solar tank should be up to 4 times cheaper than a conventional storage system over a 20-year period, and 8 times over a 60-year period, but also last 2 to 6 times longer. 8 years of monitoring, laboratory tests, and prototypes is proving that SolarTank is working as planned. SolarTank prototypes have been in operation and continuously monitored in 2 households over the last 10 years. So summarizing the benefits of SolarTank. What are the improvements of SolarTank over traditional solar water heaters? That is the question. The DC or AC booster provides 50% versus 10% of solar contribution midwinter. If on the smart meter using daylight energy, it is actually 100% renewable energy for the grid at 8 cents per kilowatt. All the boosting is done off-peak, day or night, and when combined with the extra solar contribution, the saving is about $2 to $6 per day, depending on water use. This amounts to 120 to 360 savings midwinter energy bills in temperate climates such as Perth. In spring and autumn, the solar contribution for SolarTank is 85% versus 50% for traditional solar systems. In summer, it is 100% versus 90% for commonly used solar systems. The tank never overheats as a result of excess solar exposure, as is the case with traditional solar water heaters, adding years to the life of the tank. Over the full year, the solar contribution is 85% to 100% versus 60 to 70%, which is ideal in Mediterranean-type climates, the general range being cool to warm temperate climates. The design is adaptable for all climates with modification to some of the components. Basically, it uses more solar energy and is more cost-effective. SolarTank has a much cheaper boosting regime than what is possible with traditional solar water heaters. Costs? It should be around $1,000 less than the usual cost of installation. Supplied and fixed, and only take 1 or 2 hours to install. Maintenance is negligible and will last a very long time. It is twice as good economically and lasts 2 to 4 times longer. It will be cheaper when mass-produced. Comparing with gas or electric storage units, it is 8 times as good economically when looking at the real cost over the life cycle. It can also be connected to existing PV systems. Let's take a look at the facts behind the MassLink air conditioning system. Research carried out in 1993 confirmed that reductions of 30% of energy bills is attributable through passive solar design and night ventilation of thermal mass. Before going further, it is worth understanding the economic realities of PV systems. It needs closer scrutiny. PV costs currently are around 5 to 10 cents a kilowatt hour, but are coming down fast. When combining general power use of PV and of peak over 24 hours, it averages 9 to 10 cents a kilowatt hour. To understand how MassLink works, we really need to look at the coefficient performance, or the COP. This is the thermal energy generated relative to the energy supplied. For example, a COP of 2 means that twice the thermal energy comes out of 1 unit of electricity. Refrigerative heat pump systems are usually 3 to 5 or above. Mechanical exhaust ventilation, cooling thermal mass, comes to about 20 degrees or above. Direct evaporative cooling is 12 to 18, and indirect evaporative cooling is 10 to 15. So what is MassLink's COP under its operational parameters? A COP of about 3.5 to 9 and above is achievable for heating and cooling. This relates to experiments in a temperate climate range. The original thermoelectric cell was discovered between 1821 and 1836. Its function in physics is known as the Peltier effect. Since 2000, improvements in cells and the cooling of computer systems opened up creativity for the world in this area of research. The efficiencies achieved in testing have been excellent, but we have to think out of the square. We've got a 6-fold increase compared to that normally expected of TECs. This is due to the configuration of the embedded system and the management of the energy source. And it's not the only method that can be applied to energy-efficient passive solar building. It has potential uses in conventional and hybrid air conditioning systems as well. The main point in all this is the potential cost savings to building owners are immense. Current air conditioning technologies cost between $2,000 and $3,000 at peak cooling power, and recently will be rising since the COVID pandemic. This means that the life cycle capital cost implications for traditional air conditioning systems over 60 years is between $4,000 and $6,000 of peak kilowatt cooling power. Mass-link systems using TECs probably cost around $1,000 a peak kilowatt of cooling power. However, over 60 years, this would be around $1,200 of peak kilowatt cooling power. This is very, very attractive. MassLink maximizes the theoretical COPs of the TECs by reducing the steady flow temperature difference of the hot and the cold sides of the cell. It keeps it well below the 10 degrees, imperative to get the higher COPs. When applied to a new generation of energy-efficient buildings, MassLink will be a significant step forward for lowering emissions and saving energy. Most of the operational time this temperature difference will be kept at 4 to 6 degrees Celsius, and often less than 2 degrees, so it will work well. This is due to the linking of the cavity wall system, and also this is achieved by lowering the electrical power supplied to the cell, being the voltage and the current. Though applied in an unconventional way, the MassLink system is a potential game changer in the heating and cooling of buildings. The benefits are listed as follows: saving energy for heating and cooling by storing PV energy into the mass of the building during daylight hours at about 5 cents per kilowatt hour or less. Combined with night ventilation, an average COP over 24 hours will be around 12. This will reduce the energy costs of the passive solar mass cooling strategy to about 1 to 2 cents per kilowatt hour over a very long time, say around 60 years. This works out to about 30% of the life cycle costs of providing cooling as compared with traditional pump systems. Heating has similar economics, giving 70% savings. We have used 4 cents per kilowatt hour as an average for comparisons with life cycle costs of traditional systems. It has viable use as a hybrid air conditioning system with a conventional commercial plant providing solar-driven fresh air ventilation, and 60 to 75% savings during daylight hours providing there is fresh air. This amounts to 30 or 40% of the air conditioning bill in most buildings. If batteries are considered for nighttime use of air conditioning, the comparison savings using the MassLink strategy are more like 85% savings or above. So all round, the economics of MassLink are outstanding. MassLink should be around 30 to 50% of the cost of conventional air conditioning to install and maintain over a 30-year period. The Mass Wall construction system is also a Wise Earth Research Centre innovation. This has been done in conjunction with Midland Brick Limited, who manufacture brick products in Western Australia. A special wall system has been designed and is undergoing further development, based on licensed German technology, which is the core of its structural and thermal features. Other alternatives are under investigation, using green concrete filling that may improve the cost and speed of erection time. MassLink has been designed to dovetail into this new construction system. During the commercialization of MassLink and the MassWall systems can be monitored in real time over a 12 to 18 month period once a demonstration building incorporates the integrated approach. We predict that the total system will be ideal in small-scale developments, such as low-rise residential apartments up to 4 stories and smaller infill projects. Also, mixed-use, commercial, and light industrial would be a good demonstration of the total systems. The system assumes night ventilation of onward day cooling from MassLink, using both PV and of peak power coordinated by a special control system. It will deliver human comfort and negligible energy bills. The team's cooperative objective is to develop MassWall as an alternative construction system for more widespread adoption later. Projects are currently being identified, and a new thin brick is being developed for the external skin of the wall. Once these technologies have been completely verified and the JV construction formed, we will be ready to start building and integrating our technologies. Meanwhile, they can be demonstrated in buildings already built in a variety of climates in Australia as a comprehensive trial. All our technologies planned for this commercialization phase. A plan for integration into the Swanbourne Precinct Development Trust project, which originally was to be known as Ilios, which is Greek for sun. However, delays and economic circumstances have forced us to apply the technologies in another project out at the Bayswater Precinct as part of the Innovation Drive project. Another planned project identified for ongoing demonstration is the Railway Precinct at Swanbourne on the commercial strip. Once these projects get approved, they should be a catalyst for further integration for infill development by the industry generally. Commercialization starting with provisional patents have been submitted for both SolarTank and MassLink, as well as other IP protection has been assured. We have been granted patents now in most manufacturing locations. Wise Earth has been operating for many years under the support of the federal government Research and Development Tax Concession Scheme. It has placed our team in a very strong position, as all aspects have been explored before starting a full-on commercialization process. Strategic allies, collaborating universities, and industry partners are now being sought. We envisage a period of intense work of 3 to 4 years once the capital has been raised. Joining the team for the commercialization phase is Tony Fitzgerald, who was a former MD of the famous innovation company Orbital Australia. He plans to be an advisor to the board once the capital is raised. He has been a co-director along with Professor Wasim Saman from UniSA, who reported on the initial testing. A restructure of the board will occur once the participants in the commercialization have been decided. Thank you for watching. Please watch out for our next video about the World Renewable Energy Conference that was held in Perth in 2022.